It's recording. Pick a thing here. All right. So I'll do a quick review of this Jupyter, and then we're just gonna kind of wrap it up. We did most of the work last time we met. Okay, so today, hopefully, we can get to complete the pipeline and then start doing some additional architectures. And really the key thing here is beyond what we did last week with the classes and everything that was object oriented. The second objective would be to get an understanding of the performance metrics, how to measure performance, and then how to build architectures, right? So if you remember, we did linear regression. So my goal would be now to do a multi-layer perceptron, right? So, and then also deep learning, right? So, and just show you how that can be done in a very straightforward way, okay? All right, so let's review where we are. I'm going to click on kernel and restart and clear the output just to kind of start and kind of orient myself as to where we left off. I'll move this. Okay. All right, so we load the libraries. Obviously, we're using NumPy, Torch, Pandas, sklearn, and then we have the specific modules to build neural networks, which are torch.nn, torch.nn functional, and torch optim, basically. Okay, we also have some libraries, matplotlib for plotting, mlextend that we also use for the heat map, sklearn that we use for model selection, the train test split, and then also torchutils.data. From it, we use tensor data and data loader, right? So I showed you guys that was important for loading our data efficiently. Then we have the parameters, batch size, learning rate, and number of epochs. Okay, so these are parameters that might change. And, at the end of the day, we want to achieve really good results in our predictions. We need to start measuring that performance. So far, all we know is that the loss did go down up to a certain point, right? But we don't exactly know how well the model is predicting. Okay, so that's what we have to do today. We have to use the model, and we're going to evaluate the model on the test set. So it's being trained on, I believe, almost 4,000 samples, and we left 1,000 samples for testing. Okay, so that's what we're going to do. All right, so we've got the parameters. We read the wind data using pandas. We view the data, and we know it's all numeric, but it's not normalized. So that's another issue that we may want to address, right? How to normalize the data. Then we've got the headers list, right? And we, for some data science or data analytics, we did a correlation matrix that we discussed already. After that came the very basic approach of just going from pandas data frames all the way to torch tensor. So we did to NumPy, right? Then we printed out the shapes, and we can see that we have initially 4,898 samples, right? We need to do slicing here. Okay, and we view our data. And then this is really important here. We split the data into the X data and the Y, X matrix and the Y vector. Then we do the train test split. And once we print out the data, notice that this time around, this is what I was saying about the poor man's tenfold cross-validation, right? So if I had left 42, we would basically repeat the same experiment that we did last week. Do you guys see that? But because I have this nice line here of random, right? Then this time around, we've got a different train and test set. Do you see that? And so this experiment might give us different results. But what's important is repeating this multiple times, about 10 or so, and then you start seeing a pattern. Does that make sense? And then you can always choose the best model. That's a thing that people do. People will run 10 models and then go with the one that they think, oh, this one seems to be the best. This is a common practice. All right, and saving the models, in fact, is common, right? So you can do, eventually we could do like a cell where we just save the model. Save this, every time we run it, we're saving it with a name, And then we know that it was iteration 7 that we liked, and we choose that one to be the one to use. So that's a very common thing to do. All right. But anyway, so my point is we are now, in theory, getting a different set of training and test data. Okay. This is I mentioned that sometimes you get this error, float 32 versus float 64. So you correct it by just making the data sets float 32. And then we converted the data into torch tensors. I haven't normalized the data yet, but I'll probably show you how to do that today. Okay. And so we'll get to that. Then we created the data loader. Okay, and that should be done now. And I showed you gave you the very first example of how you build architectures using object-oriented programming by inheriting the class NN module into your own class. Okay, and this is a very standard approach to doing this. Okay, and actually, I would recommend that you do it this way. All right, all these cells are because we're going to be adding new architectures. And here's the training loop, just to go over the training loop. If you look, it's exactly the same as the training loop we did before for the Celsius to Fahrenheit. Except that we got 2 for loops now because of the batching. We use the model, predict on X, get Y pred, then calculate the loss function, Y pred between Y real, and that's the loss. And then we just, zero out the gradients, do loss backward, and then opt step. And that's, we pretty much always do that. All right, and then here's our model. And then when we do this, the model is going to start training, right? So we're all caught up. And so now we're going to talk about the next steps. Let me here. I'll let it run for a little while. You can see it still, goes from 46 and then 0.5, 0.29. I don't know if we got a 0.29 the last time around, but keep in mind, if we get better results, it could be because we have a different split on the train and the test. All right, so the first thing I'm going to do is start writing the code for standardizing the data. So this is the idea of normalizing our data. Okay, so we're going to do that. All right, so this is going to go on, I think we did 1,000 epochs, right? So this is going to take a while, it seems, every time we run this. So let's cut the number of epochs. This is, huh? Sorry? I'm gonna reduce it to like 200. Just so it's a little bit faster, okay? Because we're gonna be just writing code and we want to see what's happening and, update things. So let's just do 200. We're actually 100. All right, we can always go back to 1,000. Okay, that should be more than enough. Okay, so I did 100 there. Now let's go down here. Yeah, and that's going to be a little bit faster, right? Okay, so while it's doing this, let's go to the whiteboard. And let's talk about standardizing the data. So this is the process of scaling the data or normalizing the data. So the idea is that we're going to have hold on, it's not working great. Okay, sorry. I don't know why that was not working, but it seems to be working now. All right, so standardizing the data is a very simple operation. Okay, so you have X, let's call it scaled. And really, this is the result of the data here. So minus the mean of the X's. So let's say X mean. Sorry? Yeah. X mean divided by the standard deviation. So it's going to be the X standard deviation. Okay, that's it. So this is all we have to do. Okay, so the approach will be basically to create two variables that will calculate the mean of the X's and the standard deviation of the X's, and then we're going to perform this operation. Okay, and that will allow us to normalize the data so that we can convert the data from this to this. So in a vector space, if we look at this, the effect of standardizing is, for instance, we may have three axes here, right? And this axis may go from 0 to what? To like 200,000. Whereas this axis may go from 0 to 4. Do you see that? And then this axis may go from 0 to, I don't know, 15. Do you see that? So really, when you think about the vector space will not look like this. Instead, the vector space would look really like, this, and then this one would be just that big, and then that one even tinier. Do you see that? So when you have data in something like this, one of the axes is going to dominate the rest. And you don't want that in machine learning. So what you want to do is you want to normalize or scale or standardize the data so that the axes are all equal like this. So the transformation, basically, you could say that what happens is that it converts the data to the same ranges. All right, the same ranges. So when you normalize, it goes from 0 to 1, 0 to 1, 0 to 1. Or when you standardize, it goes from like a -1 or -2 to +1, +2. Okay, so it depends on it, the ranges are a little bit different. We'll see that. So normalization and standardization. So the range would be from 0 to 1 or from about, I think it's like -2 to +2, centered at 0. Okay, so we'll see this effect. And this, either one of these approaches works. They both work really well, and people use one or the other. I'll show you this one today. The equation for normalization is also very straightforward. So it's very simple. Okay, but let's just do this one first, standardization. Okay, and create the variables. Any questions on this idea? All right, so let's go back to the Jupyter notebook. All right, so as you can see, it finishes more quickly. So somewhere along here, so this is going to be very interesting because we're going to calculate this data here, but then we're going to actually try to perform the operation inside of the class. All right, so we want the normalization to happen inside of our neural network, although it could also happen outside. Okay, so it's either, it's a choice, but I'll give you this example today. So let's create the variable. So let's call it x means. And we're also going to create y deviations. Okay. So we have to think about this. Now, train and test are pretty much the same, right? That means it doesn't matter the number of rows, but the number of columns is the same. Okay. So then we only need to calculate the means for the trained data. We wouldn't calculate it for the test data because the test data can change. When we deploy our model into the real world, we don't know the test data. Okay, so the way to do this should be, we have our variable here, x train tr, and because it's a tensor, it already has a mean function. And we're going to do x train underscore tr dot mean, and then we're going to say that we want the means across the x-axis, right? You guys see that? So we want it across the x-axis. Huh? Yeah. Oh yeah, tr, sorry. Okay. And then let's say keep dimension equal true. Okay. Now let's also one thing that happens since we're dividing, if you remember the equation, we're dividing by y deviations, okay? And it could turn out that the y deviations are pretty small, right? And you never want to divide by 0 because it's going to give you an error, right? So it's a good practice to have a little epsilon variable. And this is also something that we should specify as a parameter. So I'm going to say epsilon. This is just like a precaution. So epsilon, let's say 0.00301. So it's just big enough so we don't get like an underflow error or divide by 0 error, not a number, but also small enough that it shouldn't affect our result, right? So we can do that, hit run. And now we're going to go back. Okay, and we're going to do y deviations. So it's going to be the same. We're going to invoke x train underscore tr. And now we're going to do dot the standard deviation function. And we're going to specify that we want to do this for dimension 0. Keep dimension equal true. Equal true. And we're going to add that epsilon just so, as I said, so it's not too small. All right, so let's run this one, and then we're going to print them out. Okay, so I ran it. Now let's do x means. Okay, so as you can see, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 values in there. Our x vectors are of size 11, and this is the mean of all in the train set. Got it? Any questions on that? All right, and then we're gonna do the same. Let's add a new cell. And we're gonna do this for y deviations. And it should be very similar. So we should have 11 values in there, and these are the standard deviations. So now these are the values that we're gonna use in the equation. So it's gonna be the x minus mean divided by y deviations. And that should scale, and it's the standardization approach to our data. So that now all the axes are gonna be consistent instead of some being bigger than others. Does that make sense, guys? This is important, and it should provide good results, or better. It's what I can say is that you always, most of the time, let's say, this will give you better results. Okay, so we'll try it out. Okay, so now we have those two variables. So now I want to test my model again with this. So I'm going to go to, we're going to go to the linear, so to this area here, to the architecture, and we're going to try to modify it a little bit. So if you notice, X comes in, right? The X train comes in and it goes into the linear model, basically the neural network of 11 inputs to 1 output. And basically you do a prediction, right? But the data is not scaled. So now what we want to do is we want to take in the X data and scale it, right? Or standardize it with these parameters, and then just see if that improves our results. So let's go ahead and do that. So how are we going to do this? So when we create our model here, so I'll start with this part, right? So when we create the model, now we're going to provide to this the X means and the standard deviations, yes, as parameters. Okay, so the names we gave it are, yeah, X means and Y deviations. Okay, so we're going to pass those in. Like that. Does that make sense, guys? Yeah? Okay, so this is a convenient, why am I doing this? Why am I doing this here like this and not outside? Yes, but why? There's a specific reason why I'm doing it this way. Like I could, so think about this scenario. I could take the X's outside of this model, right? The architecture, and normalize it. But then think about this. What's going to happen when we deploy this model? You're going to have to normalize the data before you feed it into the model. Do you see that? So you will be left with writing that code in the deployed version. So by doing it this way, we don't have to do that. We can just give it the X as is, and it's going to normalize it inside. Okay, so this is basically the idea. All right, so let's go ahead. We've got the X means and the Y deviation. So now we need to go into linregnet and modify it a little bit. So in init here, in the main init function, we are now going to pass those parameters. So we're going to say X means, comma, and Y X deviations. Oh, I called it Y, right? Yeah, that's it should have been X, sorry. Not sure why I did that. So make this modification. Sorry about that. Yeah. And then, all right, so then down here, yeah, this should be X, don't run this one yet. And then in the definition of the object, it'll be X means an X deviation. So we pass the parameters, okay?
I do have a quick.
Yeah, go ahead, please.
Would adding a hidden layer for neurons make it more accurate? Or
Possibly,
Possibly.
possible. We will do that.
Okay. That sounds something I'm on.
Oh, no, right. I mean, this is just a linear regression, so it doesn't have any non-linearities, right? So we have to do that. But I'm starting here. This is the simplest approach. And also normalization is really important. So
That's the more important step.
huh?
That's the most.
No, all of these are important. So normalization is important. Obviously, more hidden layers is important. The learning rate is important. More epochs is important. More data is important. All of those things can improve your results. Okay. But yes. So currently I'm just, one of the things I want you to understand is how to create these architectures, right? Using this object-oriented approach. And as I said, the reason why I'm doing the operation here is that this makes it very convenient when we deploy the models. Okay. Because we really want to make our coding outside of this very minimal. Do you guys see that? And so putting it in here makes it easier. All right, so what do we do now? We need to create variables inside, right? Because in the init, we need to define all the variables that we're going to use in the forward. So now we can do self dot x means. And of course, we assign to it x means. That's the vector. Remember, it's a torch tensor, so it should everything be fine because it's going to load into the computational graph. Then we do self dot x deviations. And it's going to be equal to x deviations. Okay, got it? All right, now that's the definition. That's all we need to do. So now we just need one step here. Before we load the x into the linear one model, we're going to standardize. Do you see that? So how do we do that? We just follow the equation. So it should be what? X minus, yes, self, right? Self dot x means divided, very good. Self dot x underscore deviations, exactly. This is really great because, if you just have one sample, this will work. If you have 5 samples, this will work. And when you deploy it, it should work, right? So we'll talk about that at some point. I don't know if we'll do that today. Don't forget, you need to create your GitHub accounts if you haven't done so already, so that you can deploy this to GitHub using Onyx when we get to that point of the class. Okay. All right. So, and you'll see that should be pretty straightforward. All right. So we've standardized the data with this operation. And yeah, so now instead of feeding the x as it was, we feed the x after this operation, and it is now the scaled version of it. Okay. And so that's it. So hopefully, let me double check that I didn't miss anything. Yep, that's it. All right, so now let's run this code again. So you should load this again, right? So we updated it. And now let's, the training loop does not change. And we can now, so let's look at the performance. So the performance was 6.6, 0.3, 1.5, 0.59. So let's see if that improves anything. 26. Two, 8, 4, 5. Point 6. 79. Point 33.
Well, I got a whole class.
Oh, yeah, okay, so we don't know. But, let's just trust that this will be useful later. I mean, if we run it for more iterations, I leave it to some of you that are curious, run it for more iterations and let me know if it does better, right? So anyway, this is one thing that is almost always guaranteed to give you better results, right? In a tough data set, if you don't have normalization, the first recommendation is add normalization. Got it? All right, perfect. So that's incorporated now. And so now the other thing we're gonna start thinking about is before we add architectures, we need to have better metrics to evaluate performance, okay? So I wanna have better metrics for that. And so what I'm going to do is I'm going to add some code to evaluate the test set, okay? So we're gonna think about that one. So let's do it down here. I think we had evaluate model. Any questions, guys? Okay. No improvement? Did anyone try it? No? Did it go into 0.0 something?
Like 0.03 is the lowest.
0.03?
No, 0.3.
Oh, 0.3. So, okay, so yeah, so no improvement. All right, so now let's do evaluation of the test set. So the model is this one, right? So the model gives us Y-pred. So then now what we're going to do is we're just going to give it the test set instead. So what was the name of the test set? So X test TR and Y test TR. X test TR. So that's uppercase. Right, so let's do Y-pred test just so that we have something. All right, so let's run that. Okay, it ran, right? So let's take a look at the shape of Y-pred test. And what do you think the shape should be? 980, 1, right? So basically then, let's see. We need a way to evaluate performance. So this is where we're gonna use sklearn again. sklearn. Okay. From sklearn dot metrics we are going to import a nice function called r² score. Okay, so that's the name of the module in sklearn. This metric is the standard metric used in regression problems. Okay, so when we do classification problems, we're going to look at another set of metrics called precision, recall, F measure. But that's when you have classes, like I have cat, dog, etc. But here we're not predicting cats or dogs, right? We're predicting numbers, like real valued numbers. So that's a regression problem. And for that, we need a different kind of metric. And there's like a couple of metrics or a few metrics that you can use, but basically R² is the best one. Okay. So this is called officially, it is called the coefficient of determination. And basically, we're going to learn how to interpret it, okay? And just to kind of see what it does. Also, I believe if I remember correctly, this only allows NumPy as an input. So we're going to have, this is where we have to detach our results from the torch graph so that we can run it. All right, so I've added this. Now we're going to go back here. And we have to think a little bit about printing out this metric, the R-square. So what R-square does is it's going to compare the predicted with the real. Okay, so it's going to do that. So we already have the predicted because we gave it X test TR, 980 test samples, right? And it gave us Y pred test, the predictions. So if we print Y pred test, should have, right, so these values, you can see the values are not exactly integers, but they are in the scale of 0 to 10. Do you guys see that? And then we're going to compare these to the values we have. Now, one thing we could do is we could make these int and just round them. That's something we could do, but let's just try it like this. Does that make sense? Yeah. So we're going to compare these. Okay. So to obtain the R-square should be just one number. Okay. So now we're going to say print, let's call it testing R-squared squared. Okay. Space, and now comma, and now we're going to invoke R-square score, the actual function that we just got from sklearn. Now, there may be other ways of doing this. As I said, there may be other functions that you can get from PyTorch, etc., to calculate R-square. I'm just using the one in sklearn, okay? Okay, so I'm going to do this without, just so that you guys can see the errors, okay? So let's do, it would be Y pred. This will take two parameters. Position shouldn't matter. So it'll be Y pred test, right? Y pred test. And should be Y test TR, correct? Y test TR. This will give us an error. Okay, run it. Okay, so let's read the error. Can't call NumPy on tensor that requires grad. Use tensor detach.numpy instead. Do you see that? This is a very common error that you will get when you're trying to run a torch tensor that's still attached to the graph. Okay, so we got to do the detachment and then convert it to NumPy. Does that make sense? Okay, so both of them, I think, are actually attached to the no, actually Xtest is not attached, right? Yeah, so only one of them is attached. So let's do then Y test TR should only require us to do NumPy. Okay, because it's not attached. But this one for sure is attached. Okay, because it came from the model. Yeah, the model, right? So then we can do detach as the recommendation said, and then detach as a function. dot and then numpy, basically. Does this make sense, guys? Why we're doing this? Any questions? All right, so let's go ahead and try it. See if it errors out. Okay, no error. Minus 1.46. That's not a good R square. Okay. Huh. That's not a good R square. All right, let's do one more thing.
Wait,
Yeah.
It might actually be reversed, because for me, it's saying that our score takes the Y true and then Y side. So it might be reversed. Because I flipped them and then I got 0.3.
You did?
Yeah.
Why would it matter? I mean, I see your point, right?
But yeah, I know it's the arguments.
Because let's see, let me think of what you're saying. So but when I've done this before in my example, I did pred and then real.
The linter on my VS code for our two scores says exactly what you just said.
That it's an error that.
Well, Y true should be first and then Y pred should be second.
Okay, no, I don't disagree with you guys. It just, my code over here worked. All right, so let's see. So you're saying I should do this, right? Let's see what that does. So Y test tr numpy, and then Y pred test detach numpy, get rid of that. Okay, let's run it again. Yeah, 0.28. That's not great as an R square. So I don't like that. Now, this data has something I don't like actually, which is the fact that those values are scores from 0 to 10, but they're all integers. Did you see that? It's like they're 6, not 6.3. They're 5. So I want to try something. Just converting them. If we convert it, Yeah, if we convert them to integer, for instance, or round them, that could be could improve the results, because the values in real are integers and the values here are not. Do you guys see what I'm saying? So that's something we could consider to see if the R square goes up or down. Let me actually also get rid of the standardization. Let's see if I actually made a mistake here. So if I just do this, right, all I'm doing is I'm commenting out the standardization, and I want to run it without it and see what it gives, because now I have a better way of evaluating performance. Let's train the model again, this time without standardization. And like I said, I haven't run this data set, so I don't know what the best performance is of it. All right, when you do your homework assignments, your goal is just to make it as good as possible, but you may not know how good you can get it to be. Okay, that's machine learning. Okay, so it's gonna finish in a sec. All right, so now let's run the R square again. $20. So what's your conclusion? Standardization made it better or worse? Worse? Why? R square is 0.20 here. What was R square before? 28. So you want the higher R square. Huh? You want the lowest. No, that's not an error. This is not the coefficient of determination. So this is with R square, you want the higher value. So, okay, so I didn't say that maybe. Did you guys think we were minimizing an error, right? That's why you said, okay, I got it. This is not an error like the loss function. Sorry, I should have said that. Before, we wanted to minimize. So when we print that, so that's a good point. When we're doing this, we want to minimize, we're minimizing the loss, right? We're bringing it down. But R square is not, it's a different metric. And here what we want is actually the opposite, to take it as high as we can to 1. Okay? Make sense? Does that make sense, guys? So I know, for instance, then, that the model here, which gives me 0.20, is worse than the other model that gave me 0.28. So I'm going to go back and add in the standardization. See what I'm saying? So I'm going to go back into the architecture. See, I'm adding this in. Okay. So here we want to minimize this loss for sure, but we want the R square to be higher. Okay. Any questions? Does that make sense? Now, with R square, with this, you can get weird R squares, like that negative that we got. And that actually is an indication that there's something wrong. But once you start getting good results, you know, you want it to be pretty high. So you can get it all the way to 1, and that's pretty good. Okay. All right, so let's let it think a little bit. Okay, so it's almost finished. All right, so it finished. Now we're going to check the model again. We want to beat that 0.20. Still not pretty good. Still not good at all, actually. But standardization does improve performance. Any questions?
Like what is 0.20 and what is 0.2? As you earlier said, like R2 score is just to compare the values, like predicted values and real values.
Right, it compares the predictions to the real. That's correct.
If I'm getting 0.20, what does it mean?
That it's better. It's just a metric of like how good it is
The values
compared.
are actually correct.
Yes, how, you know, the higher it is, the better the prediction. The closer it is. So remember, you have the real and the predicted, right? That's what you're giving it. So this is a way of comparing models, basically. And so if you did another model and that model gives me 0.35, then that's the better model. And if I did another model and that model gives me 60, then that's a better model. So for instance, I'm just saying, let's say I do a deep neural net and then this one achieves 0.28. This is linear regression. I don't expect it to be very good, right? I think Lenny said this, right? So what would be the next step? A multi-layer perceptron. No, you know, because there may be some relation. So this is the idea. There may be some relationships in this data set that are nonlinear, that require a different kind of an architecture. And that's where neural networks come in. So the neural networks may be able to capture something that linear regression cannot capture. And so when we do another model, a multi-layer perceptron or a deep neural network, right? If they're better, we'll know because the R square will be higher. So if we get a model that's like 0.98, it's really good. Does that make sense, guys?
Yeah.
Now, how will you know that now there's an additional way of you knowing that this is good, right? And that way is basically to print out the results and compare them to the real, like manual inspection. Do you see what I'm saying? So this data, as I said, has a thing that I don't like, which is that the original data is integers and the predicted data seems to be real numbers, right? So we can either like convert those to integer and see, you know, if that's better, but also we can try different architectures. So let's go ahead. That's the metric that we will be using for regression models. Okay, there's only a couple of things I want to do. So let's see. One thing I want to do is to print the losses, and that should be not too hard to do. Another thing I want to do is print the actual values. Okay, so how do we do that? we've got. So we've got Y-pred test. Dot shape. Okay, and we also have Y test TR. Dot shape, right? Right. So what I want to do is I want to basically print these side by side and look at them. This, I would recommend doing something like this. So we got to think about how to do that. And then there's a little trick we can do of plotting a graph to compare the predicted to the real. So this is like a very fancy way of comparing the results. So we're going to build both of these things next. Okay. So you guys can help me out. So we're just going to do a for loop here. For I in range. And we're going to do length of one of these two, right? So length of test TR. Okay, so if we do this, copy, just gonna corroborate. Right, that gives me 980, right? So, or you can hard code it, but all right. So I just want to make sure I don't make a mistake there. All right, so now we're just gonna print the values. Let's do something like that. Oops. Okay. And then we can say print pred versus real. Okay. And then now we want to print our values. So let's say np.real is going to be what? Y test TR I dot detach should be like that dot numpy. Okay. Do you see that? All right, so I'm getting the NP real. So and then I'm gonna try to print it. Yeah. So this should be print NP real. Let's see if this works. Okay. It's working, right? So this is the real value. And now I want to print the pred value. But I'm going to want to print them side by side, basically. Let's do comma. And then here we need to provide the predicted one. So that would be, what is it? Y pred test, right? Y pred test. Let's detach it. Dot numpy.
NP underscore real underscore.
Oh, yeah. Oh, that's right. And then, oh, yeah, so the way I was doing it was, so let's do NP pred, right? Just to be consistent. Y pred test, then would need an I. Yeah? You guys agree? Okay, so then NP pred. Okay. So we can see the values are being, it's 5.9 to 6, 6.01 to 5. So this starts to give us an idea, right? That it's not predicting so perfectly. You guys see that? But overall, this is 6, this is 7. All of these are in the 6s and the actually. What do you guys notice just by looking at this data? Look at it really, look at it for a while. They could be rounded up, right? So that's one thing I was saying. So inherently, this is one is integers, the other one is real numbers, right? And that's not something that's good. The other thing I'm noticing is that the numbers, I don't see any 3s in the predictions, but I'm not seeing any in the real data either. I see a 7 there, which is and then this is a 6. You see what I'm saying? So this isn't a Joey, do you have a
What?
did you observe something? You
Well,
seem like you're gonna say something.
They're all scores and people tend to not score below like a 6 or a 5.
Okay,
That's
so
why you're not getting a 1, 2, or 3, or 0.
in the scores.
Right, because
Okay.
it's a score.
So there's nothing in the data that, okay, all right. Oh, valid, okay. So then we need to improve this. That's my point, right? So we're currently working the problem. These are the tools that you can use to, to try to understand the problem and try to improve it. One other thing we're gonna do is we're gonna collect this data in a couple of lists. Okay, so now this still gives me a NumPy array here and an array here, right? They're both in NumPy arrays, and it's giving me the float value and everything.
Try removing the bracket in the last one, in plain statement.
Uh-huh.
We have double brackets, right?
Yeah.
Instead of that, give only one bracket and parentheses.
Remove the brackets. Okay. Yeah, but they're still in here. If I do. I'm trying just to get the values here. Let me do. Yes, that gives me. Okay. Right, gives me the values. So that should be just the values, right? Hopefully. I'd like to put a parent. Oh, that's easy. Okay, looks a little bit nicer. So this is our results, and this is something that we can do. We also, I'm gonna basically show you a visualization tool, because what's the problem with this? You gotta look at it, you gotta scroll down. gotta think, right? And we don't want to think, right? So I'm gonna show you a visualization tool for this, to look at this data in another way, I guess. So what we can do is we can create two lists. We're gonna call them list threads. And we're just gonna initialize it to nothing. And then list reals. And also initialize it to nothing, but they're two lists. All right. And then as we are processing the data, we're gonna add it into these lists. Okay. So now I'm gonna do list threads dot append, and we are going to append into it np thread 0. Okay, you guys see that? Now again, I don't know how to make this R square better, to be honest, right? So we're gonna just throw everything that we know at it and see if we can get it to be a little bit better. Okay, so but I'm showing you the visualization tools right now that can maybe help us to do that. So we've got list reals dot append, and we're gonna add to it np real. Yeah, like that. All right, so this should give us the two lists. Let's just run it. Okay, so now that the two lists have been created, let's add a cell, visualize test predictions. Okay. Okay, and so now we want to use that. Okay, so I'm gonna create a function here, define plot threads versus reals, let's call it, which will take as input the list of threads, comma, and the list of reals. Okay, so we're going to define this function in a second, and then we can call it from here. So control copy like that. Okay, so this is, it's going to be a matplotlib type of a thing to visualize our results. Any questions so far? Okay. Right, so let's think about this one. All right, so we're gonna do a plot, so PLT dot figure big size equal, and let's just pick a size for now. You can play with this later. Okay, and then let's use the PLT dot plot. Okay, and let's do List reals. List reals. Hopefully this will work. List reals, comma, label equal real, comma, color equal red. Okay, let's try that. And then let's do plt dot plot list spreads, right? Spreads. And then label equal spread. Okay. All right. So let's leave it like that for now. We can always add more things like a title and so on. And let's do plt dot show. Let's just see what happens. So I'm gonna load the function and then try it. Okay, that's a thing. So this is what I sort of want, but it's not great, right? Do you see that? So what are we looking at here? This is a nice tool I mean, this is definitely a nice tool. What would you want this tool to show? You would want this tool to show only one color in a perfect world, right? Why? Because that means that both the red and the blue are the same prediction and one covers the other. So, but since we see two colors, what does that mean? It means that it's not a great prediction. In fact, red is probably the real, I want to say, and blue is the predicted. So if you notice, the predicted is somewhat stuck here, like, right? And it's not going towards the more extremes. Do you see that? See how this tool gives you some nice information that we didn't have before. Okay. So our goal is to see how we can improve this. Now we have, all right, so this is a good stopping point. Let me just kind of conclude this part. So what have we done today? We mainly focused on what? How to measure performance, right? So we had a loss, so I'll recap. We had a loss function. That's what we had calculated before. We added the standardization, which I believe does work because the R square went from 0.20 to 0.28. Okay, so this is this part. We added the R square. Now the R square could also be calculated on the train set. So that's another thing that might be recommended, right? That we want to look at it on the train set because it could be good on the train set, but bad on the test set. So that's something to consider. And then we also showed how to take the model once it's trained, load it with the test set, do some predictions. We've got the R square here, 0.28, as we've stated, we don't want it to be 0.28. We want it to be 0.90, 0.98, you know, higher. And we also found a way of printing out the data, the pred to the real, comparing it, and then basically we created this visualization tool to kind of view all of it in one shot. Okay, all right, guys. So it's 6:22. We're gonna stop for a break.